What's up, guys? It's me, Sir Ernest, and today we're going to solve example 2.3 of Thornton and Marion 5th edition. The problem reads, after the block in the previous example, so in this case example 2.2, begins to slide, the coefficient of kinetic or sliding friction becomes mu k, which is equal to 0.3. Find the acceleration for the angle theta equal to 30 degrees. So in this case, our block on this inclined plane, whose incline is at angle theta, is now starting to move. So it now has an velocity equal to x dot. Okay, so again, setting the x and y directions to be along the incline and perpendicular to incline respectively. And then identifying the forces now. So in this case, the forces will now be the normal force, the gravitational force, and your kinetic friction Fk. So in this case, the kinetic friction Fk will now be equal to negative mu k Fn I hat. Okay, so again, there are three forces acting the object. You have the normal force, the frictional force, kinetic frictional force, and your gravitational force. So you can see that there are the system is relative the same in terms of mathematical expressions from example 2.2. So you can just refer to example 2.2 video to know that the x component of this motion, or the equation of motion and the x component of this system, of this problem, will be equal to x double dot equals g times sine theta minus mu s cosine theta. Okay, so in this case, the mu s component will now change to mu k because the object is now moving. So that means we cannot set x double dot to be 0 because the object is already accelerating, speeding up. So from here, we can calculate x double dot to be 9.8 meters per second squared times sine 30 degrees minus mu k, which is 0.3. Remember, mu k, or coefficient of kinetic or even static friction, are unitless. Then multiply it with cosine 30 degrees. You can just compute this using your calculator. So that's 9.8 meters per second times the quantity sine 30 minus the quantity 0.3 times cosine 30. Then just close the parenthesis and then hit enter, and the answer is x double dot will now be equal to 2.352 meters per second squared. So this is the acceleration of this object for angle theta equal to 30 degrees. Now we can have some additional analysis here, wherein we could calculate the velocity as well as the position. So if in order to get the acceleration and the velocity, so remember that this is acceleration. So this is derivative of x dot with respect to time. Okay, so that means we can integrate this to get x dot, dx dot, and then this is integral of g sine theta minus mu k cosine theta dt. Then if the velocity, remember the velocity of this particle or object starts from rest at time equal to 0, Okay, and then this is t, this will be x dot. So this will give us the expression x dot equals x dot naught or 0 if we started from rest, and then this becomes g sine theta minus mu k cosine theta t. Then integrating again. So remember, this is derivative of x with respect to time. So derivative of dx, integral of dx will be equal to integral of g sine theta minus mu k cosine theta t dt at time equal to 0. Let's say the object started at the origin, and then at a later time t, the position is at x. So integrating this, we now have x will be equal to 1 of g times sine theta minus mu k cosine theta t squared. So this is the position, the velocity and position function as a function of time of this object as it slides down, given this acceleration. So you can reduce this to your usual, for example, 2.1, wherein the frictional force is absent. So if the frictional force is absent, mu k will be 0, and then you'll end up with your original result in example 2.1, which you can refer later. Okay, so that's it. That's example 2.3 of Thornton and Marion 5th edition. Thank you for watching. I hope you learned something today, and I'll see you guys in the next video. Bye-bye.